Hello, everyone, and welcome to the Altium OnTrack podcast. I'm your host, Zach Peterson. In a moment, we'll be speaking with Lukas Henkel about his open source laptop project. But first, we have Lukas from Altium here to discuss a broader initiative to support the best open source electronics projects. Lukas, good to see you again. Thanks for joining us.
Thanks for having me.
So if you could, please tell us about this new initiative to support electronics engineers who create open source projects.
Yes, so this is a new initiative that we are just starting at Altium. And in short, we want to support engineers who create open source projects. And these people devote their time, their resources to create something for others. They help in development of technologies, but also in developing communities because they promote collaborative work. And all of this align with values that we have in Altium, which is why we want to support these great people.
So how specifically will Altium be supporting these engineers?
Well, we have a number of tools that we can use, starting from providing full access to our software through sharing our knowledge, our expertise, network of contacts, and ending with helping during fabrication of those projects. Also, we can help in I think the most essential aspect of an open source project. So make these projects accessible to as many people as possible. And that's why we are going to share our web infrastructure, where authors of those projects will be able to publish their projects, publish information about them, and even invite others to collaborate. We will be organizing interview with these authors, webinars where other engineers will be able to meet them and ask questions live. So there is a lot of options that we can use.
That sounds excellent. So what is the first project that's going to be supported?
So the first open source project that we will be supporting is an open source laptop project started by Lukas Henkel. And Lukas is a great engineer who wants to design a laptop from scratch and share this project with the community. And as we know, as you know, as electronic engineer, as I know, designing a laptop from scratch is not a trivial task. That's why we feel that we have to support this great idea.
It is a great idea. And I think the last thing everyone wants to know is where can the materials related to this project be found?
So for this project, we have built a dedicated web page in Altium Resources where Lukas will be posting all updates regarding his project. There is also a podcast you recorded with Lukas, and we have prepared a public workspace where everyone get access to the laptop projects, and they will be able to follow the development of the project. And that's all.
Okay, that's great. Well, this all sounds extremely interesting, and I know I'm looking forward to seeing what people will produce. So I just want to say to you, Lukas, thank you very much. And to everybody else that's listening or watching, stay tuned for the podcast. Hello, everyone, and welcome to the Altium OnTrack podcast. I'm your host, Zach Peterson. Today, we're talking with Lukas Henkel, owner of Open Visions Technology. If you follow Lukas on LinkedIn, you've probably noticed that he's working on a very interesting open source project, and that is all of the components for an open source laptop. I think this is going to be a very interesting topic for us to discuss, and I'm very excited to talk with him today. Lukas, thank you so much for joining me today.
Thanks for the invite. Pleasure to be here. Hi.
Yeah, absolutely. So we've never had you on the podcast, and when I heard you were doing an open source laptop in Altium, I thought it would be very interesting to talk with you because I've seen some of the posts on LinkedIn. So maybe you could tell us how you got started on this project and a bit more about your background.
Sure, of course. I'd say I'll start the story with how I got into the whole electronics business. It's a story that starts pretty early. If that's okay, I just give you a little bit of background there. So as you can see, I'm pretty young, participant of the electronics business here. I've started at the age of 10 doing my first electronics project. the first project was actually involving some kind of high voltage transformer. So I won't go into too much detail, but it was a pretty interesting start. So there's always this kind of thing that catches someone to get involved with a specific topic. For me, it was a high voltage to actually start getting into the electronics hobby that it was at first. So for myself, it was pretty clear early on that I would like to pursue a career in electronics design. And that's what I did, basically. So I did start my electronics career at Semikron. I did job training there and got into the R&D department pretty quickly after that. And so yeah, I had my first contacts with electronics design pretty early on. Started my own PCB designs pretty early on. Also, that's the reason why I've got to use the Altium Designer pretty early on. Was looking for complex designs to just learn and get into the whole how to do high-speed design stuff. Then I found the videos from Robert Feranec he has done on his OpenRex designs. And that really fascinated me. And I was just thinking, okay, I want to do something like that as soon as I have the capabilities to do something like that. So, but yeah, that was kind of the inspiration, to be honest, just watching the awesome content that's out there. Also, getting to know your podcast as soon as you started. I've pretty much followed along from the beginning on. And yeah, I wanted to definitely contribute in some kind of way. And that's why I've decided to pick a project that's interesting for me personally, but also interesting for other people watching. And I thought, yeah, laptop is the perfect example. I mean, it's a system that's packed very dense. There's a lot of computational power in a small form factor, a lot of electronics from different kind of for different kind of applications has to be integrated. For example, a touchpad, camera sensor, and so on. So a wide variety of different circuits that have to be integrated, and that's also the reason why I decided either laptop. The other thing I was thinking about was a smartphone or a tablet, but it was for me pretty clear some kind of consumer electronics. And yeah, that's the basic inspiration for the laptop project. To just contribute in some kind of way and show off a design that's a bit more complex and that people hopefully can learn from.
I think a laptop is an interesting choice because there are so many subcomponents that go into that
Yeah.
laptop. And you can say that about, the circuit board level, because I mean, there's a lot of different parts of that circuit board, but then also from the actual components. So, you brought up
Yeah.
like touchscreen or touchpad. There's the
Exactly.
keyboard. Yeah, there's the power input. There's like the webcam. I'm sure there's like
Yeah.
a little circuit board up there with the webcam and everything
Yeah,
in
yeah.
between.
Yeah, exactly. That's the thing. So for me, it's always interesting to see a wide variety of components playing together. So not just having, let's say, a single processor board or a single a microcontroller board, but just dealing with all the other stuff. So what I find, for example, very interesting is the touchpad. Designing a touchpad on my own will be very difficult, but that's the challenging part. It's the interesting part, I think. Because there you have to bring in all sort of other modeling techniques. So you have to think about signal to noise ratio. You have to really build a finite element model of the capacitive touch sensing structures themselves. You have to optimize those. You have to connect them to your touch sensing IC in a very low capacitance way. So you have to make sure there is not much, I'd call it parasitic capacitance in this case, to ground, because this, of course, will impact your signal to noise ratio and stuff like that. So there's a whole another rabbit hole to go down, let's say. And I'm really looking forward to exploring those. Other example might be the battery pack. You have a bit of power electronics in there. Power electronics also in quad marks, but definitely a very wide variety of of subcircuits, and I'm really looking forward to integrating all those.
So for someone with your background, did you find that the electrical side or the mechanical side was more difficult to deal with for this type of product? Because I think sometimes when people jump into open source projects, they're focused on just one side of it, and they do that one side of it really well. But then when you look at the other side, it might not make so much sense. So like, for example, like they'll do the circuit board and they'll lay out a really great circuit board, but when you try to put an enclosure around it, it's not very sleek. It's probably a bit boxy. So what did you think? What was the most difficult side of that type of design?
Well, that's a good question. I think we will see. To be honest, at this point, I can't really tell because I don't even have the first prototypes ready yet. But there is definitely a back and forth going on. So it's not like I'm designing the PCB first, then design the mechanics around that, or the other way around. It's basically taking place in parallel. And I think in order to design a system that's the best compromises out of both worlds, the PCB and the mechanics world, I think that's really the only approach to start these designs in parallel and iterate and find the best solution forward. But I can definitely say mechanical side is a bit more challenging for me because I'm an electronics designer and not really into the mechanics side of things too much. So this is definitely a great learning experience for me. But there are a lot of things to take care of, especially for a laptop project where you have the need to design a product with a good look and feel. So the enclosure has to be stiff enough. It can't warp or flex too much. You have to take care of the thermal management. So where do you place the heatsink in the enclosure? How do you design the heat, the airflow of all the components so that all the components get optimal cooling solution? And figuring out stuff like that, at least for now, was pretty fun. And I think the first prototypes will definitely be a great learning experience because I doubt that I got it right in the first try. But as an electronics designer, the mechanical part was definitely more challenging for me so far.
Yeah, that's interesting that you're doing the mechanical portion and the electrical portion in parallel because, some of the folks that I've worked with on those types of projects where you have to fit them both together, they start in one domain, they set the constraint, and then they push it to the other domain. And I've done it both ways too, where you have a mechanical person who gives you the enclosure and says, this is what we're going with. You have to fit in here. Here's your keep outs and things like this. And then the other side where we kind of have carte blanche on the board, and then we have to give it to the mechanical person and they have to create something manufacturable around it.
Yeah, definitely. I mean, of course, these are valid approaches and these are very successful approaches. That's also the approach I had to take with my former employer. But I think you're in some cases restricting yourself too much with that approach because there might be some solutions that are somewhere in between the middle. So you have to apply some changes to the circuit board, but you also have to apply some changes on the mechanics side. But the solution, the overall solution coming out of that approach is better suited for your application. And yeah, that's why I decided to not fix one domain and push it, or let's say force it even into another domain, and basically saying here, that's what you got to deal with. Because I think, as I've said, there are solutions you're leaving on the table by just not exploring these paths in parallel. And yeah, the other thing is, as I'm a one-man show doing this project, I really have no other choice than to go about these things in parallel at the same time, because otherwise, I'm pretty sure I won't be finished within the next few years.
I think also if you start in one domain and then push to the other domain, it kind of relies on one of those designers to like see the future. So like if you start in mechanical, they have to be able to see into the future as far as what you're going to do with the electrical design. And unfortunately, that doesn't always pan out. So
Definitely.
it's almost like sometimes the optimal solution doesn't really become obvious until like maybe you get partially through the board and you put it in the enclosure, and then you realize, oh, we can do this thing differently and get to a better result.
Definitely, yeah. Then you just design your circuit board and realize, this component is getting pretty hot. Maybe it would have been a good idea to place it on the side, maybe couple it even directly to the enclosure to get the heat away. But as you've said, some of these things only become clear once you're far in the process, and then you have to be flexible about it. And I think that's in my opinion, the only approach to get the best solution out of both worlds.
So one thing I wanted to ask about the mechanical enclosure, are you planning to do this through 3D printing, or is this going to be like sheet metal, or is it going to be molded plastic? What are you thinking?
So I'm aiming at designing the whole thing as a aluminum body. So this will be a part machined completely out of solid aluminum. This isn't really the most environmental friendly approach, I'd say, and also not the cheapest approach, obviously. But the thing is, prototyping something like injection molded parts can be very expensive. The tooling costs are very expensive. Of course, there are some other ways you could go, like a vacuum casting, for example, just to get a good look and feel for your future injection molded part. But for a small project like I'm doing, and for the small quantities I plan to produce for the first run, I go with mostly machine parts because they are just cheaper to prototype in a smaller volume. And also, I think most modern laptops, especially in a higher price range, they come with a solid aluminum case because you have a good look and feel that the enclosure itself is really rugged and doesn't bend a lot. So I think the aluminum enclosure is the best way for my project for now, at least. If I maybe go into a larger production run, then I definitely think about larger or more complex injection molded parts also.
Sure, and I'm actually talking to you on a laptop that has an aluminum case, so
Yeah.
I agree. Probably probably an optimal way to go. Also, I would think that with 3D printing, because if you were going to do 3D printing, you would need a very thin layer of material, and some of those 3D printed materials can be quite brittle when they get so thin, and they could crack very easily. Whereas with machined aluminum, you have, like you said, much less propensity to flex. And if you did happen to drop it, it's certainly not going to shatter the case.
Yeah, definitely. So I do have some smaller 3D printed parts in my design also. Probably the first update will also include a few pictures of some very nice 3D printed parts. But as you said, these parts, they have to have a pretty thick wall, so at least 1.5 millimeters, just to minimize flexing also during production, because the thinner the walls get, the more they're prone to warp and flex during the curing process. So at least if you're going for a resin 3D print, which is I think the only way if you're really wanting to print parts that are visible to the end user, because parts that are printed on a filament printer, you'd have to apply a lot of post-processing, so sanding or just some way of generating a good surface finish. You don't have to do these extra steps with an SLA print, for example. But I definitely do have some 3D printed parts in there also to make prototyping easy. And especially the 3D printing services got really cheap. So I think it also makes sense in some production environments to go for 3D printed parts instead of injection molded parts. Of course, always depending on the final quantities. But if you're doing a production run of, let's say, 100 to 500 units or something like that, then also 3D printing definitely makes sense.
So the DFM rules around working with like a machined enclosure or a 3D printed enclosure, how did those affect the electrical side of it, or the electrical DFM, and what you can do on the board? Because like you mentioned, the two kind of have to play together. Yeah. And in the stuff where I've done, where we do the board and then the enclosure person kind of comes back later, they're almost like cleaning up our mess, if you think about it. we didn't really design it with their input in mind. We just say,
Okay.
here's the board and it has to fit and we have to have these features. But
Yeah.
outside of that, you figure it out. So
Yeah.
if you're doing this in machined aluminum and you have, some elements of the enclosure driving the design, how do you deal with that? How do you deal with the DFM restrictions that come from something like machined aluminum enclosure?
So the good thing is there isn't besides mounting hardware and besides cooling hardware, there aren't a lot of interfaces between the two domains. So the electrical domain and the mechanical domain, they're pretty well separated. A difficult problem that I have to figure out is really the flex of the enclosure itself, because the PCB, of course, is directly mounted to the enclosure. So all these forces are also going to be transferred and distributed onto the PCB itself. So strategically placing mounting holes, for example, and doing elasticity analysis on the board in combination with the enclosure is definitely a thing that has helped me a lot in order to see where do I have to apply more material thickness, for example, on the enclosure. And that's also, I would say, the solution to a lot of these DFM problems. Because the stiffness of the enclosure, for example, imposes the design requirement that you have a certain material thickness, and this thickness, at least for my application, is a lot larger than the minimal requirement for the manufacturability. So a lot of these issues have canceled them out so far on their own, luckily. But one problem I'm facing, for example, is with the heatsink. So you need to have a heatsink with a very high pin density or fin density to carry away a lot of heat on a small volume. So for forced convection, you can place these fins very close together, in contrast to just naturally convection cooled heatsink, where you have to place the fins very far apart in order to let a convection current form on itself. But there the question arises, how close can you place these fins together, and what manufacturing techniques can you employ to actually manufacture this thing? And that's definitely something that's a challenge, because there are basically only two ways. You can design a zipper fin heatsink manufactured out of sheet metal, or you can design I think it's called a skived heatsink, where you have a solid block of aluminum and you basically come in with a knife, cut or carve out a thin sheet and bend it upwards. And that's definitely something where the manufacturing capabilities place some restrictions on the design, because I would like to design the heatsink as small as possible in order to not take up PCB space, but I have to adhere to the design rules of the heatsink manufacturer. And I have to see how to balance these two, because the PCB as it is right now is pretty crowded. So let's see how that turns out.
Yeah, the PCB and laptops are typically crowded, but you brought up something interesting here, which I think sometimes folks forget about unless they have to do this kind of mechanical modeling and look at things that the elasticity of the board, which is strategic placement of mounting holes, with the goal being to dampen or prevent vibration at some of the most critical parts. And so I'm sure that's going to constrain where you can put the CPU, where you can put some of the connectors, so on and so forth. Yeah,
definitely. So what I've done so far in terms of modeling these things, of course, I've modeled the flex of the enclosure itself just on the normal use. So you're carrying this laptop around, I don't know, maybe if you have the laptop in your pocket and you're throwing in your bag and you're throwing it back around, your laptop is going to experience some mechanical shocks, of course. But there's the other thing, as you've just mentioned, with dampening oscillation modes. I've tried to model the natural frequencies of this enclosure together with the PCB. So I've done a model analysis to see, okay, where do we have resonant peaks on the PCB, where are the highest magnitudes of oscillations, and which components can I place there and which components shouldn't I place there. I mean, something like that is more critical for automotive application, for example, where you're going to see a wide spectrum of frequencies and also a pretty high amplitude of those frequencies. For consumer application, this isn't that critical, but it's definitely something to keep in mind because you can't rule it out in the final application. And stuff like that definitely influences where you can place the mounting holes and also how you mount the PCB. Because well, if you mount it directly to the enclosure itself, you basically have the equivalent of a tank circuit with a very high Q factor. So we actually want to have some rubber washers under there that can dissipate some of this mechanical energy and some of these oscillations. And yeah, these are very interesting topics to look at. And luckily, there are open source tools out there that allow you to actually model and simulate these things.
And you just brought up another interesting point here, which was the coupled oscillations between the enclosure and the actual circuit board, which is another thing I think that folks might not consider. And it has such a simple solution. Just throw some rubber dampers on it.
Yeah. Well, just some user experience implications, because you have a fan in there. This fan, of course, will cause some vibrations, and as this fan is speed regulated depending on your PC on your CPU temperature, you're also going to have a pretty big spectrum of frequencies you're dealing with. And if you have some resonant modes in there, you're going to hear that. And these resonance modes can either be in the mechanical parts of your enclosure, or the other resonant mode that you can have is in the air volume. So just like blowing over the top of a bottle and hearing a frequency depending on the liquid level, you're also experiencing these resonant modes in the air volume within your laptop, depending on the rotational speed of your computer fan. And this is also something you can, and in my opinion, also should model, because I've had a lot of laptops in the past that were quiet for the most time. But there was a frequency not even at the highest speed of the PC fan, but somewhere in the lower range. But the humming got really amplified and got really annoying at some time, because there was some kind of resonant mode within that laptop somewhere. And yeah, that's definitely not something I would like to have for my design.
So on the mechanical side, how do you optimize that type of thing? Because, I mean, sometimes you deal with this in signal integrity. There are just so many geometric parameters to look at, and there are so many levers that you might want to start pulling to try and eliminate one of those problems. Like I see it in, via transitions for high-speed signals all the time. And then you see it sounds like all over the place in the mechanical enclosure for both acoustics and thermal and mechanical vibration and ability to withstand mechanical shock.
I mean, that's a pretty complex optimization problem. There are definitely commercial tools out there that could tackle that problem, and they're actually built exactly to optimize such complex problems with many input variables. There is a way also with the use of open source tools to optimize stuff like that. So you can actually tell your preprocessor to alter the geometry to mesh it new geometry and perform a new simulation run. That's possible, but that's only possible on one variable, unfortunately. So comparing these different solutions and comparing the impact on each domain is still a manual process. And yeah, what can I say? It just takes a lot of iterations and a lot of time. And probably some of that will also take place during the prototyping phase, because I'm sure looking at all the different variations and all the different variables ahead in simulation isn't possible for such a large project. There has to be a prototyping stage that definitely will uncover some of the problems you have not seen in your design phase.
Yeah, absolutely. It's great if you can simulate it, but eventually you have to correlate that back to some level of testing. One round of testing that I could see going on here that's pretty important is EMI or EMC. Do you plan to put this thing through any level of EMC testing, or at least just EMC pre-compliance before, something that someone might do before they actually take it over to an anechoic chamber?
Yeah, definitely. So I have some pre-compliance equipment, at least for checking on the board level. I have a TEM cell that I can use, and since I plan to manufacture a small batch of this laptop, of course, I will have to go through the whole product certification process. So going through the EMC test lab, then there is the thing of the RED certification, because I have some wireless equipment in there. LTE, for example. Well, I'm not quite sure if I'm going to use LTE, but of course, Wi-Fi is definitely a must. And for stuff like that, there is a whole certification chain that I have to go through, definitely.
Certainly. So just to back up for a moment, you mentioned that you were formerly at Semikron,
Yes.
and I understand they're a German power electronics manufacturer. Is that correct?
Mm-hmm. Exactly, yeah. So Semikron focuses mainly on the large IGBT or large, well, not exclusively IGBT, but mainly large power modules. So catered for the, I'd say, power classes above 50 kilowatts. There are also some smaller devices used in washing machines, for example. But so yeah, basically high power electronics semiconductors.
So what was it like transitioning away from that side of the industry to, I guess, doing your own thing and getting more into PCB design?
Um, well, there wasn't, or the transition wasn't really abrupt, because I've started my own company in parallel to my work at Semikron pretty early on. So my own company and Semikron, they've lived in parallel for about 3 years. So the transition was really smooth, and the stuff I've done at Semikron was in some cases also pretty similar. So I wasn't in contact with the whole power electronics side. I was more in contact with the IGBT gate driver side. So I was part of the team that designed the gate drive circuitry for all the power IGBT modules. So there were definitely some parallels between my day job at Semikron and the company I've built in my spare time, basically. But the challenges, of course, were quite a lot different. At Semikron, you have to deal, of course, with PCB design for high voltage applications. So you're taking a lot more care of creepage distances, different types of pollution degrees you have to keep in mind. You have to run extensive analyses on partial discharge, for example. So all this kind of stuff that you don't really have to deal with when you're doing digital electronics. But yeah, I think I've seen how the power electronics industry worked, and I wanted to do something new, something different, at least for me. And that's why I decided also to move on to more digital electronics, because it's a topic I haven't had that much contact at my day job with, but I found to be very interesting. And so, I was looking very much forward to building my own thing and doing more the high density designs, the more multi-layer designs, and stuff that you just don't see in power electronics generally.
Sure. And I'm sure that running your own company and essentially doing engineering services, it gives you a lot more variety of projects.
Yeah, definitely. So that was that was a really nice experience, because at the beginning we didn't make that much marketing. Nowadays, pretty much um, the contracts come in based on the content we put out, let's say. But at the beginning, there was a much more variety in the project requested that we've gotten, and That was definitely very interesting. Yeah, we had a lot of different subjects to deal with, like acoustics, for example. That's not really something that I had contact before, but also a very interesting topic. That we had a customer who went more into the optical side of things, who had to deal with laser assemblies and stuff like that. And then we had a customer with precision measuring equipment, so all over the board. But yeah, that's definitely a very cool thing about the whole engineering services business, that you just see topics from all over the industry.
I agree. That is always nice. You can be picky sometimes and you can
Yeah.
choose the things you want to do, but you also get a pretty good amount of variety. Do you ever get anything weird coming through the door or totally infeasible coming through the door?
I have to think about that for a moment. Totally infeasible. Well, of course, some customers come in with totally unrealistic expectations. Yeah, but so far we have managed to come up with a solution that we are both satisfied with and that are also physically possible. I mean, we also had customers who would like to have basically a hologram, which I said, well, of course we can talk again once the physical basis is there for that. But as of right now, sorry, can't do anything for you. But other than that, I think most of our customers have a pretty clear picture in mind of what kind of system they're aiming at. We have some customers who don't really have or have had contact with the electronics or mechanical industry. So they just have an idea and come to us and say, hey, can you build a product that does this and that? And with these kind of customers, it's always a bit difficult to really work out the requirements that are realistic and are also manufacturable at a sensible price point. But as I've said, so far there was nothing that we couldn't find a good solution for.
One group of companies that I have tended to deal with over the past few years has been startups. And it's always been interesting because a lot of folks at these startups are actually not hardware people. I've noticed, at least, for the companies here in the US that I've had to deal with, they actually come from software and they have a great idea, but they know it needs some kind of piece of hardware in order to support it and implement their application. Yeah. Is that something that you see where you have people coming and wanting to build a piece of or a device, an electronic product, but they don't have that background to really understand how to get into it?
Yeah, definitely. That was what I was talking about, having customers who just have an idea but have really no way of knowing how to make that actually happen. Not just from the technical side of things, but also from the side of things when it comes to certifications. So a lot of our customers, they look at our quotes and ask, hey, what's this action point certifications and why is this so expensive? And then you just have to go through the whole bringing a product to market cycle, basically, and explain what has to be done, what's involved, and how expensive is it really. So that can be a bit difficult from time to time, because a lot of the folks coming in didn't really expect for product development to be that expensive. But well, that's something that every engineering company is going to tell you. So yeah, you have to make that work somehow from the client side.
I think sometimes people will look online and they'll see, oh, I can buy a Raspberry Pi for $10. Why do I need to pay all of this money for something custom? Circuit boards can't be that expensive, can they?
Yeah, exactly. And then you have to explain, okay, well, this is a product that's been sold in the million pieces or even more, that has gone through all the certification life cycle. I mean, and if you have a business model that focuses really on hardware that is going to be sold in large quantities, then a small in quote marks, small investment at the start doesn't really matter too much. But for customers who haven't had previous experiences with bringing hardware to the market, of course, this knowledge and this experience isn't there. And so you have to walk them through the whole cycle, basically, and tell them how that works.
Yeah, absolutely. When someone's coming in with a plan to eventually scale to tens of thousands or hundreds of thousands of units, they're certainly more willing to invest on the front end in very competent engineering services. And I think they're much more receptive or even thinking about these ideas of certification. Whereas, somebody who wants to build 20 or 30 boards, they may not even realize that EMC certification or UL certification or any of these other, certifications are even a thing they have to worry about.
Yeah, exactly.
Yeah, a lot of customer education for sure, and something I can relate to you on.
Yeah, that's a good way to describe it. Customer education. I like that.
So, with the open source laptop, can you show us an example of something that you're working on?
Yeah, I can show you some designs I have open right now.
Okay, that would be great.
Share my screen real quick.
So to anyone that's listening, I'll do my best to describe what we're looking at.
I hope you can see Altium Designer open now.
Yeah, we have Altium Designer open, and just based on the large central component with a lot of pins coming out of it, looks like we have a BGA footprint for your CPU.
Exactly. So what you can see here, what you can see here right now is a preliminary design for a motherboard. We have one central component, as you've noted, that's an IMX8 8M Plus processor, to be precise. Together with various peripheral components. On the top, you can see a DDR4 DRAM IC. On the left side, there are two QFN packages. One of those is an Ethernet PHY, the other one is a USB hub. And on the right side of the processor, there is a smaller BGA that's a Pericom, or now Diodes Incorporated, I think they are, a PCI Express bridge. And what I've designed here, I'll just jump into 3D mode real quick. This is basically a system on module. So for my first design, I thought about integrating a system module instead of a dedicated motherboard. The benefit of this approach would be, of course, you can swap out the system on module pretty easily in case a new processor variant comes along. You can maybe even design the carrier board with a lower layer count and with not so strict design rules or not so strict requirements on track width and track spacing, so you can make the carrier board cheaper while keeping all the complex PCB technology in the SOM itself. But the problem with this approach is just integrating it into the enclosure without making the whole system larger or the whole laptop thicker. And that's definitely something I would like to have, to design a thin and light laptop, and that turned out to be pretty difficult using a system on module approach. And to be honest, that's something I could have seen coming even before designing this whole PCB. But I thought it's definitely a good idea to get a bit more into this workflow on how to customize your image for this IMX processor, for example, how to bring up such a board and stuff like that. So that's why I decided to follow through with that. The bring upness now is pretty much complete. I have still some things to sort out, and there are still some learnings in there that I can also apply to my to the open source laptop in the, let's say, new concept with the integrated motherboard. And but I decided to follow through with this design just to apply all these learnings to my open source laptop project. And now I'm thinking about also open sourcing this design just as a single board computer, basically, if you will, for people to take a look at and to see how I've gone about designing a board like that.
And so real quick, if you could go back to 3D mode for just a moment. So what we're
Sure.
looking at here is we have basically all of the compute needed for the system on this one module, as well as several connectors on the bottom layer. I see a couple connectors
Exactly.
on the top layer as well. And
Yes.
then this would interface with a baseboard, I'm going to assume through like a mezzanine connector or something.
Yes. Let me just flip the board view here. So there on the side, we have the two board-to-board connectors that provide most of the available interfaces to the carrier board. So for example, we have three PCI Express interfaces, four USB interfaces. We have eMMC interface also routed through these board-to-board connectors. But as you've mentioned, I also placed some of these connectors, as you can see here on the left. There are two USB-C connectors on the left, one mini HDMI connector in the middle, and an industrial Ethernet connection on the right. I wanted to have these connectors also available on the board itself because I wanted to be able to bring up the system module without the carrier board so that you can also use it standalone. At this point was also thinking about other projects that may benefit from a CPU module like that. And so I wanted essentially to have a way to play with this board without the need of a carrier board. That's why you can see some of these connections on the SOM itself. And
I think that makes a lot of sense because someone could take this and they could build their own baseboard around it for whatever other type of system they want to build, not just for a laptop.
yeah, exactly. That's also a good segue, I would say, to another board I've also designed for this laptop project. I'm going to jump in 2D mode for a start. It's the same processor. It's also the IMX processor. So what you can see right here is actually a board in the Raspberry Pi form factor. Jump to the top here real quick. So this is the Raspberry Pi CM4 compute module form factor. You have basically the same peripherals and the same pin out as it comes with the Raspberry Pi itself. On here you have the SoC, the memory. In this case, it's 8 gigabytes of DDR4 memory. You have an eMMC on there, Wi-Fi interface, so all the peripherals that you would also see on the CM4 module itself. So this could be a retrofit solution. In case you want to swap out the Raspberry Pi for an IMX-based solution, you could also do this with this board. And I've designed this because I have my own application that currently uses the Raspberry Pi that I would like to substitute with this board. And I'm also thinking about open sourcing this board. Unfortunately, I'm not quite there yet with the bring up of this one. But I'd say, especially for the enthusiast community or the hacker community, having an alternative would be interesting. I know there are a lot of CM4 alternatives out there. But the good thing about the IMX processors from NXP is they have a very open documentation. So you can get everything you need directly from the manufacturer, which can be difficult with the Asian brands, for example. Thinking about something like Rockchip or Allwinner, getting documentation for these ICs can be very difficult, and you have the benefit of NXP just openly providing all this documentation needed, which can be very helpful in case you want to spin your own design using an IMX processor.
That makes a lot of sense. So on this board, we're in the Raspberry Pi form factor now. We've eliminated some of the connectors that were on the previous module. And so now we're looking in 3D. And I can see that the layout doesn't look too aggressive, but there are several chips on here that all have to interface with each other. So I guess going with the Pi form factor was helpful here because you're still at least able to fit everything on the top layer. Or most everything on the top layer. That's critical for the implementing computing.
Yeah. So all the active components are placed on the top side. I do have, of course, some passive and the decoupling capacitors, as you can see right here on the bottom side. But other than that, on the bottom side, you can only see the board-to-board connectors in the typical Raspberry Pi compute module fashion, and also an additional test port to connect VNA to match the antenna structures. But other than that, there's, I'd say, plenty space available on this form factor, at least for this CPU. So there is also no need to go for HDI stacker, for example. So what you see here is a PCB with all through-hole vias. And the only thing I've done to make some room and to make routing easier for myself is to use filled and capped vias, so they can place vias in pads, which comes in really handy, especially when layouting this processor. You can jump back into 2D mode for a second. So zooming in on the processor pinout itself, you can see that most of the vias are directly placed under the pads, which made routing on the inner layers a lot easier. But other than that, it's basically a pretty standard layer stack. This uses 10 layers at the moment with two signal layers, with two inner signal layers. The rest is all plain layers or ground layers, so power or ground layers. And the rest is just your standard 100 microns trace spacing and 100 microns trace thickness design rules.
Well, this is great. It looks like for both of these modules, you don't need highly specialized, and therefore you won't need highly expensive fabrication capabilities. Looks like the biggest requirement is just plug in or fill in cap for the vias.
Yeah, exactly. Yeah, that's basically all that was necessary. And on this board, you can see it wasn't as critical to use capped vias as on the other board, because other than the pin out of the SoC itself, I haven't really utilized much of the via and pad process. But I've chosen this process because this PCB is manufactured on the same panel as the previous PCB I've shown. So matching the two technologies, of course, made sense in that scenario to just save some production costs.
Sure, makes sense. Well, thanks for showing this. We're getting up there on time a little bit, but one last thing I wanted to ask you is, what else is on the horizon? Do you have other open source projects that you're planning to do after this, or maybe open source projects that you would really like to do after this is completed?
There are definitely projects I would like to do. For now, I definitely focus on the laptop project because I think the laptop project on its own will definitely take up a lot of time. But once that's done, I'm thinking about also an open source smartwatch, so staying within the consumer electronics industry. That's definitely something I would be very interested in, because you're shrinking the electronics even more. There's even more packaging going on. There's probably complex rigid flex PCBs that you can use that basically fold into the enclosure that you're designing, and something like that would be very fun to explore. But I think for now I'll stick with the laptop project. I'm guessing it will definitely take around a year to get the first functioning prototype up and running, depending on how I can sort out the software side of things. But I definitely have some more ideas for projects coming after this one.
Well, as this eventually gets to prototype, or as you move on to something else that's very interesting, we'd love to have you back on to chat about it.
Yeah, sure. Looking forward to it.
Great. Thank you so much. To everybody that's out there watching and listening, we've been talking with Lukas Henkel, owner of Open Visions Technology. To everyone that's watching on YouTube, please hit that subscribe button. Make sure to leave your comments and questions in the comments section. If you're interested in learning more about this project, all updates will be made available in the public space and on the project webpage. You can also find more information in the show notes. Thanks again for watching, everybody. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.